Hi everyone. In this video, we're going to go over Chapter 8, Regression with Time Series Data. So in today's lecture, we mainly focus on the kind of issue we have when we run regression using time series data, how we detect that, and how we estimate the model when we have time series data. Now, we talk about time series data for a while before we turn to regression analysis. In time series data, the most significant feature, or one of the most significant feature, is that the data are kind of related. The current observation usually is related to past observation. Current sales is related to sales in the past. So we call that autocorrelation. Current value is related to value in the previous period or in the previous two periods, etc. So that's called autocorrelation. Just to give you some review, here are a few more examples. The first one, an increase in salary may affect your consumption in the current and future periods, right? When you have a salary increase, you tend to increase your consumption now. You also tend to increase your consumption in the future because you know in the future your income is also higher. So in that sense, the current consumption is related to all future consumptions. And the second example is a change in price may affect sales in the current and future periods, right? When you change the price, sales will change in the current period, but all future periods, the sales will change as well. So this just shows when we have time series data, current value is related to past value. When we have such data and run regression analysis, it turns out it's not as easy as what we did before. Either it's multiple linear regression or simple linear regression. A big assumption is that the error terms are independent. Remember, we have this residual check, the 4 graphs, 2 of them are scatter plots, 1 histogram, to check if the conditions on residuals are satisfied. And one of the conditions is that we require the error term to be independent of each other. That is, they're random. There's no serial correlation. Now, when we have time series data, though, that usually is not the case. That is, that condition is usually violated. So here's some more details about what's going on when we have time series data, how the error terms are correlated with each other. So if you look at this equation, that's our typical simple linear regression model, where y is the dependent variable, x is the independent variable, and beta 0 and beta 1 are the coefficients to be estimated using the data. And lastly, the ET, that's the error term, right? And we usually require and assume the error term to be independent of each other. That is, the current period error term is not dependent on other error terms. Now, when we have time series data, though, there's usually what we call first order serial correlation, which means error term in the current period is directly related to the error terms in the previous time period. So we call it first order because it just says error term in the current period is related to the error term one period before the current one. Okay, so that's first order serial correlation. Mathematically or in equations, it's shown here. That is, ET is the current error term is equal to, and this E or epsilon t minus 1 is the error term in the previous period. So if you take this equation as another simple linear regression model, you can see that the current error term is equal to the previous error term multiplied by a slope plus an intercept, right? So it's a straight line indicating that the current error term is related with the error term in the previous period with a slope rho, especially if this rho is different from 0. Then we have first order serial correlation. Think about it. If rho is equal to 0, then the error term in current period and in the previous period are not correlated, which means we go back to our simple linear regression model we learned before. The condition of independence error term is not violated. We're good to go. Now, if rho is different from 0, that means the error terms are correlated. Then the condition of independent error terms is violated, and we need to do something about it. So before we talk about what to do with it, let's look at two things. Number one, the consequence of this serial correlation. What happens if we have serial correlation? And then number two, we want to know how can we verify that there's serial correlation. And by the way, not all regression using time series data will exhibit the serial correlation. So we need to verify, or in other words, we need to examine whether the serial correlation is serious enough for us to be concerned. So the consequences are three things. The first one is that when you have serial correlation in the error terms, or when you run regression using time series data, it can make unrelated variables appear to be related. And this will give you the misleading information. So here's an example to look at this graph here. You can see two variables, x and y. The top one is the y, and the lower one is x, the dependent variable and the independent variable. Okay, how these two variables are generated? Actually, they are generated using computer software, and they're generated in a way that x and y are not correlated at all. They are just random values. Now the problem is, since these two are generated in a way that is in order, so it started from the first period, second period, continue like that. So they are time series, although they're random and they're not supposed to be related. But since they are both time series data, when you run regression using x and y, it turns out x and y are highly correlated. So this will give you the misleading information, because although when x and y were set up, they were not supposed to be correlated. But when you run the regression using data, the data will show you, or the model will show, that they are correlated. If this happens in practice, in reality, and you use it for decision making, then you will make the wrong decision. You've got the wrong information. Okay, so that's one problem. And it is a serious one, because there are a lot of times when we run regression model, not only are we doing predictions, we're also looking at the relationship between y and one or several x variables. Maybe we want to know whether skills is an important factor of people's income, right? So we have serial correlation in the model, then the results we got from the model is not reliable. Number two is that the standard error underestimate the variability. We didn't talk about the standard error much when we go over regression analysis. What it means basically is that, well, the standard error measures two things. Number one, how well the model fits the data to a certain extent. Standard error basically measures the deviation between your estimate using the model and the actual data. So when there's serial correlation, the standard error underestimate the variability, or in other words, you underestimate the deviation between your prediction and the actual data. So making the model seems to be a good one, but in reality may not be a good one. And the other thing that the standard error related is actually the third consequence we have here. When we perform hypothesis test, we always use p-value, but this p-value actually involves using standard error. Although we didn't go through it because we didn't really calculate the test statistic that will be used to calculate the p-value, but the standard error is used in calculating the p-value. So if the standard error is underestimated, then that means we tend to have a lower p-value, allowing us to be able to more likely to reject the null hypothesis. Okay, in that sense, the T and F test will not be reliable because the standard error is underestimated. So these are the three consequences, and they are serious consequences, which means we do need to, number one, detect the autocorrelation in our regression, and number two, correct it if we have one, right? So first, how do we detect that? How do we determine if we have autocorrelation? There is a test called Durbin-Watson test. Durbin-Watson test is still a hypothesis test. That involves hypothesis, test statistic, p-value. Unfortunately, is not here. There is reject region, but I will have more to say about it. So start with the hypothesis. These are the hypotheses for the Durbin-Watson test. The null hypothesis says rho is equal to 0. The alternative says rho is greater than 0. Okay, what does it imply? So let's go back to the original model that we just looked at, right? The first equation is the regular single linear regression model. And the second equation allows us to examine, explore the relationship between every term in the current period versus every term in the previous period. And if they are correlated, we will find this rho, which is the slope in this equation, to be different from 0. And therefore, the null hypothesis rho equal to 0 tells us there's no serial correlation, or there's no autocorrelation. On the other hand, if rho is greater than 0, that tells us there is autocorrelation there. Now, the test statistic, we usually don't go through the calculation, but just for your information, test statistics is called DW here. It's equal to 2 times 1 minus the correlation coefficient. This R here is the correlation coefficient between the every term. This R parenthesis E just measures the correlation between every term in current period and every term in the previous period for every pair. Okay. Unfortunately, for Durbin-Watson test, there's no p-value. So one thing we do is we rely on rejection region approach. We do have threshold. It shows here if the Durbin-Watson test statistic, or DW, is greater than D of U, we will conclude that the null hypothesis is true. If the DW is less than D of L, we will conclude that the alternative is true. So DU and DL represent the upper limit and the lower limit. Okay, so in other words, if DW is greater than the upper limit, we conclude that no is true. If the DW is lower than the lower limit, then we'll conclude that there's autocorrelation. So to find out the threshold for DU and DW, we need to use the table in your textbook, which is table B6. At this point, I do not intend to introduce more table, but this is for your information. There is a table for you to look at the criteria, to look at the threshold. We also have a rule of thumb that you can use when making judgment. When DW is close to 0 or DW is greater than 2, that indicates we tend to have autocorrelation issue, or we have serial correlation. Okay, but when DW is close to 2, then there's no autocorrelation. So you can use that rule of thumb. If DW is close to 2, then there's no serial correlation. If DW deviate from 2 a lot, especially deviate towards the lower end, which is close to 0, or towards the upper hand, which is much greater than 2, then we tend to say there's autocorrelation. Of course, when the judgment is kind of hard for us, especially if we have a DW of 2.5, what you say, right? Or especially if you don't have much experience, then you don't know how much more is enough for us to say, oh, this DW is definitely much higher than 2. We should declare there's autocorrelation. Then we could go to the table. So let me show you one example, one application where we look at the DW and make a decision as to whether there's serial correlation or not. It says, suppose an analyst is engaged in forward planning for Reynolds Metals Company and wishes to establish a quantitative basis for projecting future sales. Since the company sells regionally, a measure of disposable personal income for the region should be closely related to sales. Run a simple linear regression and check the DW statistics. Let me move to my Minitab. All right, so here we go. This is the data for Reynolds Metal Company. We have the years and we have sales. We also have income. That's the regional income. And we expect regional income to be related to sales. Of course, we expect a positive relationship. The higher the income, the higher the sales is expected. Let's see. So we go to stat, and go to regression again, then pick fit regression model. Okay, the response variable is sales, and the continuous predictors is income, since it's a simple linear regression model. And before we run the regression, we want to click on results. And in the pop-up window, you will see the very last item is Durbin-Watson statistic. Okay, and then click OK to have it reported. Now, by the way, we've run regression models before, and we didn't pay attention to this Durbin-Watson statistics before, mainly because number one, we didn't use time series data all the time. Sometimes we use what we call cross-sectional data. It's the observation across different persons. And number two, we haven't introduced this concept of serial correlation. So at that time, we didn't check Durbin-Watson statistics. So click on OK. Now it's our traditional regression analysis output. We have the equation, we have the coefficients, we have the R-squared, analysis variance. But at the very end, since required, we do have Durbin-Watson statistics, which is 0.87. That's basically how you get Durbin-Watson test. Now let me return to PowerPoint and continue our discussion there. Recall that the rule of thumb for the DW test is that we're gonna reject the null hypothesis when DW is close to 0 or DW is greater than 2. We got 0.87. Intuitively, I wouldn't say that is close to 2. I would rather say it's closer to 0. So my impression as so far is there is serial correlation. There's autocorrelation in the regression, and that means we do have the consequences of three things. Number one, X and Y may not be correlated, but it will appear to be correlated. The standard error is underestimated, and T and F test will not be reliable. But if we want more accurate judgment, we can go to the table, and I'm just showing you this example of the table. It's table 6 in your textbook, provides Durbin-Watson test bounds. There's the lower bound and upper bound. And to determine which pair to use, you need to, number one, determine the sample size. And number two, determine the order of the correlation we're looking at. Now, usually we look at first order correlation. So we pick k equal to 1. Now, we suspect that the error term in current period is related to the error term 2 periods ago. Then we're going to pick k equal to 2 because that's called second order serial correlation. And this n refers to the sample size. So for the data we have 21 observations. That's why we'll pick n equal to 21. The lower bound is 1.22. And the upper bound is 1.42. Now, since the criteria says if the test statistics is lower than the lower bound, we're going to say there's serial correlation, which is our case here because DW is 0.87, which is definitely less than 1.22. So we conclude that there is autocorrelation in the residues, and we need to modify the model to make it valid and useful for prediction. So, solutions. If we have autocorrelation in the residues, what do we do? Well, actually, it turns out autocorrelation is easy to detect, but hard to resolve. There are two general directions. The first one is even the harder one. That is check for omitted variables. This is actually a very big topic. The textbook provides a very good explanation as to what happens when we have omitted variables. I do not intend to go through the details, but I want to explain here right now. When we try to estimate multiple regression model, we do our best to collect all X variables that we believe are related to Y. Then we run the model to determine which X variable to use, right? Now, I said we do our best, but it doesn't mean that we can guarantee we collected all X variables that are related to Y. It could be that there are several other X variables that we just didn't realize, or there are X variables that we forget to collect. there are x variables that we can't measure, etc. For those x variables that are related to y but not included in the model somehow, we call that omitted variables. And when such omitted variables are important x variables for y, then we will result in the issue of zero correlation. So that's the omitted variable. If we didn't include those x variables that are highly correlated with y, then we will see zero correlation in our model. And once the omitted variable is added to our model, the zero correlation will be gone. That's one solution. But of course, when we have omitted variables, it's easier to say than do. In particular, how do you verify you have the omitted variable? How do you know what variable you need to use, right? So in practice, people do check this because when there's zero correlation, we do check if we have omitted variables. We just do more research, do more study to see if there are other x variables that we can collect. Now, a second solution is to do the differencing. And the solution I'm going to show you now is the second one, to do the differencing. When we say differencing, it's basically we're using the current period value minus the previous period value to take the difference. Then we run the model. First, we need to go over the theory. It might be a little bit dry, but I'm hoping that when we go over the theory, you can better understand what we are doing with differences and why taking differences can take care of the autocorrelation issue. Let's start with the original model we had. We have y equal to beta 0, the y-intercept, plus beta 1 times x1, the slope coefficient, times the independent variable, plus an error term. In the past, we assumed the error term to be independent. But when we have autocorrelation, the error term will be dependent upon each other. That is, the current period error term is a function of the error term in the previous period. And we're going to assume that they follow another linear line, that is, the current period error term is equal to a slope times the past period error term. That is described in this equation up there. So when we take difference, we basically want to use the current period y minus the past period y. We also want to use the current period x to subtract by the previous period x. Okay, so let me write down the equation for the previous period. We have y t minus 1 equal to, still for the previous period, the intercept and the slope coefficient will remain the same. So beta 0 plus beta 1 x t minus 1, because this is previous period, plus epsilon, but it's t minus 1 since it's for previous period. All right, so when we combine all of these three equations together, without showing you all the details and the steps of manipulation, it can be rearranged to be the following equation. All right, so we have y prime t equal to, the y-intercept turns to be beta 0 times 1 minus rho, plus beta 1, our original slope coefficient, times x prime t plus a new error term vt, okay? And we're gonna assume this new error term of vt will be independent of each other. There's no correlation issue with vt anymore. And y prime t, x prime t will be noted by these two. As you can see, basically y prime t and x prime t is the difference between the current period y and the previous period value of y, but multiplied by rho, while rho is the slope coefficient in the error term. All right, same for x. X prime t is the current period x minus the previous period x times the rho, the slope coefficient for the error term. Now, if you look at this new equation out there, This is another simple linear regression model. The difference is that this time it's not the original YT, it's actually Y prime T given by the difference between YT and rho YT minus 1. Similarly for X, it's not the original XT anymore, it's X prime T, which is equal to XT minus rho times the previous X value. And with this new simple linear regression equation, we're going to assume everything should be satisfied. The residuals VT will be independent of each other. If we want to estimate this new model, we can do so if we know the value of rho. That's another unknown for us. For Y prime T, once we know rho, we can calculate Y prime T. Similarly for X prime T, once we know the value of rho, we can get the value of X prime T. So when we estimate the model, we have three unknowns, beta 0, beta 1, and rho. In the past, we usually estimate beta 0 and beta 1. That's all we need. So the question now is, how do we estimate the rho, right? We're going to take a simplified scenario as of right now and say, well, what if the autocorrelation is very strong? Then we can assume rho to be very close to 1, such that we can even use 1 to substitute for rho. And that's what we're going to do. So we're going to assume rho to be equal to 1. Let's see what happens when rho is equal to 1, right? If rho is equal to 1, then when you look at Y prime T and X prime T, Y prime T turns to be just YT minus YT minus 1. So basically, I'm just taking the first order difference of YT. I'm using the current pair value minus the previous pair value for every pair. I've got Y prime T. Similarly, for X prime T, it is equal to XT minus XT minus 1. So current period X minus previous period X for each pair. Then we return back to the original simple linear regression model. We have X variable, we have variable, we estimate beta 0 and beta 1, and that's all we need to do. Lastly, let's see what happens if rho is equal to 1. With rho equal to 1, for this equation right here, we will notice that 1 minus rho becomes 0, and therefore beta 0 drops off from the model. All we have left is Y prime T equal to beta 1 X prime T plus this new error term, which is independently distributed. So that means when we take differences, the model we want to estimate is a simple linear regression model using Y prime and X prime, but we also want to make sure we're not including the y-intercept because it's already dropped off from the model. Now, finally, here's an example to show you how to correct serial correlation when we have time series data in regression. So it says here, some years ago, Fred Gardner was engaged in forecasting Sears Roebuck sales in thousands of dollars for the Western region. He had chosen disposable personal income for the region as his independent variable. Fred wanted to relate sales to disposable income using a natural log linear regression model, since that would allow him to also estimate income elasticity of sales. The income elasticity measures the percentage change in sales for a 1% change in income. Data on Sears sales and disposable income for 1976 to 1996 are collected. So this is the model. The analyst in this question was using the natural log values, taking the log of y and taking the log of x, but the concept is still the same. So the dependent variable is sales, independent variable is disposable personal income for the region. First of all, we run the regression and check the Durbin-Watson statistics to see if we have serial correlation. By the way, if you want to run this regression, then the name of the data file is called Sears. So let's go to Durbin-Watson test directly. It turns out it is 0.50. Previously, we had another example where we got 0.87, right? With 21 observations. For this example, let's see how many observations we have. The same, 21 observations. For this example, it's still first order correlation. So the bounds or limits should be the same. If we were able to reject the null hypothesis for 0.87, then we definitely will reject the null hypothesis for 0.5, because this value is much lower than the lower bound, indicating that there is autocorrelation in the residues. So we need to do something to correct the model. So we're going to take the second solution we talk about. That is, we're going to take the first order difference. Since I'm not requiring you to use the table to check the upper bound, the lower bound every time, and we relying on the rule of thumb, especially when the DW statistic is close to 2, what else do you have? Well, you can also check the autocorrelation of the residue, and that allows us to double check if autocorrelation is a problem. So let me now move to Minitab, and I want to show you how to check the autocorrelation of the residues. All right, so here's my Sears data. The analyst Fred was using the log of x and y. Now we're gonna need to create log of y and log of x for the regression that Fred is using. First of all, I want to declare the two variables. I want to create the log of y and log of x. Then I go to calculator. We want to store the result in log y. And inside the expression, we want to go to the functions in this list and pick natural log right here. If in alphabetical order, so if you pull all the way down to n, you will see natural log, which is log base e. Double click it, you get it. And then the numbers highlighted, at that time, you want to double click sales because we want to take the log of sales. And your screen should look like this. Then click OK. You will get the log of y. We want to do the same for log of x. So go to calculator. Now we'll just change log of y into log of x. And for the expression, you can go to the natural log again in this list. But what I want to do is I want to highlight sales with a quotation mark and replace that with income. Then I've got log income, which is the log of x. Click OK. And that's it, right? So the regression we're running should be between log of y and log x. So we go to stat, regression again, and pick fit regression model. The response variable should be log of y, and the continuous predictor should be the log of x. Let's do Durbin-Watson statistics, and then we also want the residues. So don't forget to go to storage, click residues to have the residues reported. All right, click OK. There we go. Durbin-Watson statistic is 0.49, which is the one I showed in the PowerPoint. So the next thing, we were talking about getting the autocorrelation graph to check the residues to see if autocorrelation is an issue in the residues. So now let's do that. We got the residue reported. The next thing is to get the autocorrelation function for the residue. To do that, you want to go to stat times series autocorrelation. The series we're looking at is the residues because we want to check if the residues are seriously correlated. Click OK. And now we're looking at this graph. So now you can see clearly there is serial correlation in leg 1, right? Just to refresh your memory, when we look at autocorrelation function like this, the way to judge if there's serial correlation or if the serial correlation is significantly different from 0, we compare the bars with the red curves. If the bar exceeds the red curve, that means the autocorrelation is significant. And apparently that is true for the first leg, which means residuals in current period is correlated with residuals in the previous period. There's only one lag, all right? So that's confirmed. And now we go back to PowerPoint and continue. Let's see how we use difference to rerun the regression and see and double check if the problem is fixed. We're going to return to Minitab really quick in a minute, but just to give you an overview of what we do, we first will need to create the difference for the variables. Then we use the difference variables to run the regression, and then we'll double check with Durbin-Watson statistic. We'll also want to check using the autocorrelation of the residuals. And lastly, once we get the model corrected, we can use it for forecast, right? So let's now move to Minitab again, okay? So what we want to do is to run the regression using differences. So here we go. I first need to define the variable. I call them diff y and diff x to indicate I'm differencing the variable. So we do calculator. First, let's do diff y, the difference of y. To get the difference of y, we need to go to the function again, go through the list, and we're looking for D. There we go. So differences, double click it. Don't worry about it. These, I'm gonna clear these words in the parentheses, differences, and we wanted to take the difference of log y. Click OK to finish it. Let's do the same thing for x. So I'm gonna go to calculator. This time it's diff x, and inside the parentheses, if you want kind of a shortcut, just replace y with x. That's what I did. All right, then click OK. So now we can estimate the model using the differentiated log x and differentiated log y. So we're going to go to stat, regression again, fit regression model. The y variable will be diff y and the x variable will be diff x. One thing we need to do though is that in this new model, actually there is no constant. When we take the difference, the constant cancels each other out. So to make the model correct, we also need to make sure the constant is not estimated. To do that, we go to model, okay? And at the bottom, you see include the constant term in the model. You want to unselect that. Now click OK. The new equation is the diff y is equal to 1.0099 diff x. Basically means the elasticity 1. So for each unit change in diff log x, there's a corresponding 1 unit change in diff log y. All right, so that's the new model. Coefficient is significant, as you can see, p-value is 0. R-square is good, it's 86%, which is good. And lastly, the Durbin-Watson statistics 1.27. That is definitely closer to 2 than to 0. I don't think autocorrelation is a problem, but just to double check, now we can use the new residue to get the autocorrelation graph. So let's go to stat time series, and we want to do autocorrelation. And the residual 1 is the new series we want. So click OK. Click OK. Now the new autocorrelation function for the residue, the new residue, shows that, yep, that's right. There's no autocorrelation in the residue because all the coefficient bars are within the limits. So it verifies that the new model is good. Now for forecast, to do the forecast, go to stat, regression, and we want to do regression again, then do predict. Just means we want to use the model which is estimated to do the prediction. Now the difference for this model and what make it a little bit complicated is that we don't put the x value for the next period for the prediction. We actually put the difference of log x. That means we require 2 periods of data to take the difference. And the 2 periods data needs to take log. I want to put 0.096 as of right now. I'll show you why I'm doing that in a minute, but just to get the prediction. So that's how we do it. Put that value for the x variable in the equation, and we got a predicted y of 0.0969, which is basically 0.097, same as x. This is not surprising because the equation basically tells us almost 1-to-1 ratio between x and y. Now I want to return to the PowerPoint slides and show you why I put 0.096 for x variable there. So this is the page showing you how to run the new regression using the newly created variables, the diff log of x and diff log of y. I just named them differently in the example I just showed in Minitab, but their basic results are still the same. It also shows here that you do need to remove the constant in the model. So here's the forecast. I do not intend to go through the whole thing because this model takes log and takes difference. It makes it a little bit complicated. I put it here for those of you who are interested. I can definitely provide more explanation. There is somewhere in this calculation shows that the value to be entered for the x variable in the new model is 0.096 with detailed explanation out there. Eventually, the forecast for 1997 is $15,029. That's the forecast of sales for Sears in 1997. All right. Lastly, the rho. Remember the slope coefficient in the residuals equation? We were assuming rho to be 1 when we use differencing. Well, in practice, there are times maybe it's not appropriate to use differencing, right? But then in that case, how do we estimate rho? Several options here. The first one is we can do a nonlinear least squares to estimate rho. The second option is we can first run a simple linear regression model to get the residuals, and then use the residue to estimate rho, because rho is basically the slope coefficient in the residual equation. Or we can do eViews. It's another computer software that estimates a lot of statistical models. It allows rho to be estimated within the model. But that's really beyond our scope of discussion in this class.